Hey, it's Cosmic Ray. We're back. The screensaver's on. L-DOPA. We started to talk before about dopamine. Dopamine. Look at all the stuff going on in this molecule. We got two alcoholic groups up here. So you think L-DOPA's stupid? He's not only one alcoholic, he's a double alcoholic. You look down here, you got a carboxylate group. This again is written in the chemical structure with the H on the O, but again, spectroscopists will tell you these oxygens here share the electron double bond between them. They're the same distance away from the carbon. So you've got a real negative water-loving tail. See, this is a great little, remember the B3 fish. The carboxylate is like a little negative electron fins and a tail hanging off there. So nitrogen, you got a lone pair of electrons up there. You got a real kind of water-loving backside of this. Carbon, carbon, benzene ring, double alcoholic on top. So again, you've got something that's loving water up here, something loving water down there, a flat ring that's aromatic, so it's stable. That ring is going to hold. So, DOPA. We were talking before about how tryptophan went on to make serotonin, one of the neurotransmitters in the brain that makes you feel good, gets you motivated, sleep. Dopamine has a lot to do with your muscle movement. So if you know anybody with a Parkinson's type syndrome, dopamine is one of the brain's neurotransmitters that isn't being utilized. It isn't being made. It isn't having enzymes regurgitate it. Something's wrong. So what a friend of mine, Oliver Sacks, found in 1969 in Brooklyn, New York, L-DOPA, the L isomer, was able to bring his patients out of a coma almost. And he called it awakenings, if you ever see the movie. But dopamine needed to get into the brain. There's a blood-brain barrier that keeps out certain chemicals. L-DOPA, Oliver Sacks found out, was able to cross the blood-brain barrier, have enzymes converted to be dopamine, that all of a sudden these people had their arms and muscles, speech back. They were sitting there a lot of the times, their brain was working fine, they couldn't move a muscle. People thought they were dumb too. So the brain can work, muscles work. So we think L-DOPA. Silicon, I like C for silicon. I like silicon. Chem is a mystery to me. Don't be an L-DOPA. Learn your chemistry and your brain will work better. That was dumb. Anyway, we're going to have to edit some of that stuff. So, back to where we were. Get rid of the L-DOPA. The periodic table of the elements in relation to the sun. These elements, the bigger the box, the more abundant it is in the sun. So if you see a lot of orange on this, helium, lots of helium in the sun. Hydrogen, lots of hydrogen in the sun. Now we were talking spectroscopically before. You can look right here at all the spectrum of the elements found in the sun. Where you see spots is where the energy is absorbed. Where you see it re-radiated, there's information to tell what elements are in the sun. And this is the whole spectrum right here. From red to green to blue. All the elements that are in the sun on this table are drawn to size. So look, lots of oxygen in the sun. Lots of neon in the sun. Fluorine's pretty big. You can look at this and not have to understand mathematics or averages or exponential notation or 10 powered to the 10 to the 13th, you can look, and what you'll see is a way to compare the elements. Huh? Silicon. There's a lot of silicon in the sun. Sulfur, argon, these are all drawn to scale. So when you look, there's some boron on the sun. So notice a lot of the smaller, earlier elements that were made in the universe here, hydrogen, sodiums, the calciums, the potassiums, the metals, the first row of metals, look at that. All those elements, all those metals are in the sun, on the sun, in the atmosphere of the sun. They're flying around, they're ionized. These iron atoms, when you look at this spectrum, this goes all the way through, red, and then there's another line of red all the way through. Where these black gaps are, these are evidence for elements. Iron has 26 electrons. Iron can have 10 electrons missing, 12 electrons missing. These are the ions at the iron atom, the nucleus, without a lot of its electrons. I've heard bare nuclei. 26 electrons were stripped off the iron. That's some high temperature. That's a lot of stuff going on to do that. So the sun is a fascinating place to a chemist. On the atmosphere, inside. So if we back up here, take two hands to do this now. For some reason, the pinky won't do it. Why can't they center it? Who designs these programs? I'm telling you, these people are idiots. They do it on purpose to drive you crazy. So we'll try and hone in on this. Lots of orange, huh? Lots of orange. So we're going to look here. What do we see? A lot of the metals. There's sodium, calcium, the rare earths. A lot of the rare earths are here. The column's going down. Boy, the red, you really can't see the red. Start getting over here, not so much, huh? Krypton, radon, don't see much on the sun. What's underneath chlorine? Bromine, iodine? Not much on the sun. What's under sulfur? Under phosphorus here, we got a little bit here. We're starting to taper off, though. Over here, we start seeing gaps. Huh? So just, in my opinion, to present a periodic table in this form, the boxes represent the size. They're actually color-coded. They go across the spectrum. So if they're red, there's more than yellow. If you notice the sizes, by the time you get to blue, they're smaller, way smaller. So look at the periodic table. There's information to be gained there. Nickel. There's more nickel in the sun than there is manganese. There's more silicon. See, it's new to me. There's more silicon in the sun than there is nitrogen. I never would have thought. There's more silicon than carbon, actually. I mean, look. So, tell me, is this a great idea? Just look at the colors. That's all you got to do. The colors are there. The size of the box. It looks cool. Kids will look at this, and then all of a sudden they're like, well, what's that? And you go, well, that's a spectrum. That's the information to a chemist. And if a teacher can't use the colors of the rainbow to make something artistic out of something so dull and mundane and black and white and one-dimensional, then something ain't right. This is our periodic table by solar system abundance. So if we look at our solar system now, And you can overlay these. This is what's great now. Okay, we got the abundances